And in this environment in which the body can rapidly be optimized for
Hello and welcome to an in-depth interview with Professor David Cebon, a distinguished authority in mechanical engineering at the University of Cambridge and a pivotal member of the Hydrogen Science Coalition. With his extensive background in the road transport engineering, vehicle dynamics, and sustainable freight, Professor Cebon has been a vocal advocate for evidence-based approaches to the hydrogen debate. In this conversation, we will explore the complexities and controversies surrounding hydrogen as a fuel, exploring its potential and pitfalls and seeking to uncover the most effective pathways for its use in achieving our global net zero goals. Professor, welcome.
Hi, nice to be with you.
Can you tell us for the start, who is David Cebon?
Well, you've given a very, very nice introduction. I'm actually from Australia. I've been in the UK for many years now. So I'm Professor of Mechanical Engineering in Cambridge. And my specialist area is actually in transport, heavy vehicles, where hydrogen is being considered by many organizations. So that has been my introduction to hydrogen has been through transportation, heavy vehicles. But from that, I've seen a lot of the other discussion about other uses for hydrogen, and I think I'm a bit concerned about some of those. I don't think they're good uses of energy and of renewable energy, and I don't think they're necessarily environmentally good solutions. So I've spent quite a lot of time investigating and researching other aspects of hydrogen, not just in the transportation area. And I was one of the co-founders of the Hydrogen Science Coalition, which is a group of academics and scientists who are concerned with providing the evidence, the scientific evidence that is needed for use adoption of hydrogen.
Talking about it, could you outline the main principles and goals of the Hydrogen Science Coalition?
I can certainly do that. One of the things about hydrogen is that actually the story is complicated. You know, there's all kinds of different aspects to it, and it's quite difficult to communicate the key ideas because there's such a wide range of things that you really need to know about to understand the topic. So in the Hydrogen Science Coalition, what we've done to try to break that down is we've developed 5 basic principles, and we use those principles for communication. So the first principle is of the Hydrogen Science Coalition is that really the only, hydrogen is an opportunity in the energy transition, but the only hydrogen that is sufficiently clean to decarbonize is green hydrogen, and that means hydrogen made from renewable electricity, and it has to satisfy various constraints. The electricity has to satisfy various constraints, but that's the first principle: is the only clean hydrogen is made from renewable electricity. The second principle is that we should the first place that we should deploy renewable hydrogen is in the places where hydrogen is used today. Hydrogen is used today for about, it generates about 2% of carbon emissions, and it's used principally for manufacture of fertilizer, for treating of petrochemicals, for some other things like manufacture of glass. In all of those applications, it's used for its chemical characteristics, and there's essentially no alternative. So there's no real alternative to use of hydrogen for fertilizer. It's about 1% of world carbon emissions. And so what we need to do first in deployment of hydrogen is to replace those applications where it's used for where there's really no alternative, and we need to replace those. Instead of with the unabated grey hydrogen which is used now, we need to use clean green hydrogen for those applications. So that's the second one, which is that we should decarbonize the sectors where hydrogen is used now. And actually, that will require a very, very large amount of renewable energy just to do that. It's a huge market for hydrogen. As I say, 2% of world carbon emissions. It's a massive amount of energy. It's something like twice as much renewables as there is in the world today needs to be built again to do that.
Wow.
So that's a lot. So that's, we think, should be the first thing, and that should be done long before any new applications. And new applications are things like powering vehicles or heating homes, powering industrial furnaces, and so on.
But shouldn't that be a natural? Shouldn't that be a natural progression in this case? So basically, starting with these industries instead of introducing hydrogen elsewhere.
Yes, with absolutely right. There is no alternative in those industries. They have to be decarbonized. They're a decarbonization problem, and that needs to be that decarbonization problem needs to be solved before we start to try to use hydrogen in other applications. So,
and can that be also basically an area for trial and error in this case, like to really building an efficient hydrogen industry?
There's no doubt that transitioning those applications to green hydrogen provides a massive opportunity for electrolyzer manufacturers and other aspects of the hydrogen supply chain to sell a lot of product, to develop a lot of product, to learn a lot about how to do clean hydrogen at scale. So there's ample opportunity within that existing hydrogen market to do all the development work that's needed for hydrogen manufacture. There's no doubt about that.
Yeah.
The third one is about prioritizing the production and consumption of locally produced hydrogen. It's very difficult to transport hydrogen. Hydrogen, where it's manufactured and used in existing applications, it's always used at the point where it's manufactured. It's manufactured in chemical plants and it's used in chemical plants. And that's essentially, it's manufactured in fertilizer plants and it's used right there. And the reason for that is that it's incredibly difficult to move hydrogen about. And that's because of its physical properties. It's very low energy density. It's very low per unit volume. It's very low mass density. It's specific properties to do with liquefying it, and very low liquefaction temperature of minus 253 degrees. All of these things make it incredibly difficult to compress and move hydrogen. And as a result of that, it always is manufactured on site where it's used, and it's never transported except for very limited applications. So the third principle actually is that we should prioritize those applications where locally produced hydrogen, and that avoids wasting precious renewable energy in making additional hydrogen that boils off, for example, in liquefaction, that in making in large amounts of energy needed to pump and to liquefy and so on. That's the third principle. The fourth principle is that blending of hydrogen into the gas grid doesn't make any sense. It has very low benefits in terms of emission saving. For example, if you blend 20% by volume of hydrogen into the natural gas grid, you only save about 7% of carbon emissions, and you dramatically reduce the energy density of the gas. The renewable hydrogen that you put into the gas, I sometimes I've got a little analogy. Blending renewable hydrogen into the gas grid is like using single malt whiskey to power your car. It's like pouring single malt whiskey into your petrol tank of your car. Single malt whiskey is very, very expensive per liter. It does have an energy value, which means that it could be used blended into the petrol tank of your car. But as soon as you do that, its value is only the same as the value of the gasoline or the petrol that you use in your car. So you go from this incredibly expensive per unit volume product, and it becomes no more valuable than the gasoline, a couple of dollars a liter or less, $1 a liter. And you've gone from something which was $1,000 a liter, or $100 a liter. You pour it into your petrol tank, it's only worth $1 a liter or $2 a liter. And it's exactly the same so it immediately loses all that value. So you can't make that work unless somebody pays you $999 a liter to do it. As a
Great analogy,
right? So it's exactly the same when you pour very expensive green hydrogen into the gas grid. The gas in the gas grid is worth maybe 1/10 or less of the value of the green hydrogen that you're going to pour in there. And so immediately you pour that green hydrogen into the gas grid to blend it, it loses 90% of its value. And so you can only do it by subsidizing it. Requires massive subsidies. And so it's a sort of a pointless thing. Why degrade the value of that valuable green hydrogen by blending it into the gas grid when you could use it to make fertilizer to replace gray hydrogen in a new application?
But the question is, why having this idea at all?
Well, I don't know. I do know, and I think it's because the people who own the gas pipes are very worried about what's going to happen to them as we wean ourselves off fossil gas, as heating systems are no longer based on gas. And so they're looking for anything that they can do with those gas pipes to make a convincing case for keeping them. And I think that's what all that blending is about.
If the world goes, let's say, to the heat pumps, what will happen with this infrastructure?
Well, I think it becomes obsolete. And I think that's a big problem that the world is going to have to address. I think that gas infrastructure will largely become obsolete. I mean, some of it might still be usable for some things, but I think it largely becomes obsolete, and we're going to have to deal with that. And those companies will no longer, the companies whose job is to manage that infrastructure will no longer have a job, and what they'll have to do is to decommission, and that will cost a lot of money. So I think, however you look at that, there's a big problem associated with the existing gas infrastructure, but it's not solved by pouring very, very expensive whiskey into the gas tank of your car. That doesn't solve the problem, by pouring very expensive green hydrogen into the natural gas grid. It doesn't solve the problem. The problem is one of decommissioning and so on. The final one of our fifth and probably our most important principle of the Hydrogen Science Coalition is that hydrogen should never be used to delay deployment of electrification and energy efficient electrical solutions, such as in heating and transport. What that means is, if you can electrify the system now, you should never delay that by waiting for a hydrogen solution in future. If you can electrify cargo vans, vans that are doing home deliveries around the city, then you should absolutely do that and not wait in case hydrogen becomes a usable solution in future. First of all, hydrogen in that same application is incredibly expensive and it's not a good solution. And second of all, it's a long way away from being a solution at all because of the problems of making the hydrogen, of deploying the hydrogen, and having the vehicles, distributing the hydrogen and having vehicles that can use it. So hydrogen should not be used to delay electrification. If you can do electrification, we should absolutely do it as quickly as possible because that's needed for the energy transition. So they're the 5 principles. In a way, that last one is the most important one, I think. We shouldn't delay the electrification. We need to go do this energy transition as quickly as possible. The best way, the cheapest way, is use electrification wherever those solutions exist.
Can you elaborate on the comparative efficiency of hydrogen fuel cells vehicles versus battery electric vehicles?
Yeah, well, happy to do that. And that's in my sweet spot, right? That's what I do all the time, because that's my background is in the automotive industry. The challenge is not just the efficiency of the fuel cell. The challenge is the efficiency of the whole process, going from renewable electricity at the top to motion of the vehicle at the bottom, if you like. I'm thinking of a sort of a chart which starts with electricity at the top and ends up with motion of a vehicle at the bottom. Now, there are a lot of steps in that process. For example, for an electric vehicle, you take your renewable electricity, you have to convert it from AC to DC or DC to AC so that you can transmit it. You transmit the electricity and there's efficiency losses, maybe 10%, depends on the electricity grid. And then you put that electricity in and out of a battery, which has an efficiency loss, and then ultimately it powers the electric vehicle. When you go through all of that, you lose about 30% of the energy, something like 30%. So 10% in the electricity grid, 15% in and out of the battery, other conversion losses, and you multiply them all together, you lose about 30% of the energy. So about 70% of the energy is available. And that is the case for any electric vehicle. So that could be an electric car, an electric scooter, an electric bicycle, an electric ship or ferry, all basically the same process. You take electricity, you transmit it via the electricity grid, you put it in and out of the battery, you put it through the propulsion system of the vehicle, and about 70% of it gets to useful mechanical work. When you do the same thing with hydrogen, you take your renewable electricity, you convert it from AC to DC, you put that into an electrolyzer, and the electrolyzer is about 75% efficient. That generates hydrogen. You take the hydrogen, you compress it, you store it, you transmit it. That's all has efficiency losses. But the real problem is that you then put that hydrogen back into a fuel cell to make electricity. And the real problem is that the fuel cell is only about 50% efficient. And you don't have any choice about that. That's the best you can do. And it's only 50% efficient because of the thermodynamics, because of the second law of thermodynamics puts a limit on the amount of, on the efficiency of a fuel cell. And because that limit is also affected by the rate of production of electricity. So the overall effect of that is that fuel cells are about 50% efficient. Now, that means that no matter what you do, you're going to throw away 50% of the energy. Now, in fact, the other processes, the process of making the hydrogen, which is only 75% efficient, you lose 25%, and those other processes, you lose energy as well. So by the time you go through all of this, and then you go from electricity to hydrogen in electrolyzer, back to electricity in the fuel cell, and then you put that into the into the propulsion system of your vehicle. By the time you do that, you lose about 75% of the energy. It's about a 25% efficient process.
Wow.
So you lose most of the energy. It has to be said, 75%, 3/4 of the energy is lost. That compares to the electric vehicle, where you lose about 25 or 30% of the energy. So when you consider the ratio of those two things, those two efficiencies, what you get is the ratio of the amount of renewable electricity that you need to provide a given amount of propulsion. And essentially the story is that you need 3 times more renewable electricity to power a hydrogen vehicle than you need to power an electric vehicle to do exactly the same task. So all of those efficiencies come out to a factor of 3 difference. And that factor of 3, you can see where it comes from. It's 75% efficient for the 75% losses for the hydrogen processes compared to 25% approximately, or 30% losses for the electric vehicle. The ratio of those is 3. So you need 3 times more renewable electricity to power a hydrogen vehicle than to power a battery electric vehicle. So to power a hydrogen truck compared to a battery electric truck, or a hydrogen car, a Mirai, Toyota Mirai, compared to powering a Tesla Model 3. You need 3 times more energy. That energy, electricity, has to be generated. You need 3 times more wind turbines, or 3 times more solar panels, 3 times more nuclear power stations. You need 3 times more maintenance. You need 3 times more land. You need 3 times more equipment. You need three times more grid connections. You need 3 times more helicopters to go out to the offshore wind. You need 3 times more maintenance people. Everything is multiplied by 3, and consequently, it costs 3 times more.
And you still need water.
You still need water. So it will cost you 3 times more to power a hydrogen fuel cell vehicle, whatever type of vehicle it is, whether it's a ship or a plane or a car or a truck. It will cost you 3 times more to power it than the equivalent electric vehicle. So it's very expensive. It's very expensive. In my area in trucking, the idea that you would spend 3 times more to power a truck is completely out of the question. Trucking companies don't have a lot of money. They don't make very big profits. In fact, on average in the industry, the profits are about 3%. So nobody can possibly afford to spend 3 times more to power their trucks. It currently costs about 40% of the budget. The 40% of the cost of logistics is energy. You can't possibly afford a system which costs 3 times more.
There's an argument for a long distance trucks, like that the battery cannot support that.
Well, that is true. There's a whole big story around that. The first part of that story is that in Europe and the UK, truck drivers have to stop every 4.5 hours for a statutory rest break. And they have to stop for 45 minutes. And there's no choice about that. It's a law. And you can, within 45 minutes, you can charge a truck on a fast charger. So within the time of rest break. And so with a high-powered charger, you can charge your truck every 4.5 hours. So that's part of the answer. It's not the whole answer to the question, but it's part of it. That in Europe and the UK, you have to stop anyway, and you can charge a truck within 45 minutes, which is the length of time of the stop. So there isn't really a problem.
In both,
at it.
yeah, in both situations, there's a need for a heavy infrastructure investment.
Yep.
So basically, we're choosing between fast chargers for batteries or the hydrogen infrastructure.
Yes, indeed. So fast chargers for batteries exist. To a certain extent, hydrogen production infrastructure exists also, distribution infrastructure. But if we look at hydrogen distribution infrastructure, we see that it's very problematic. For example, in California, business model predictions were that maintenance of hydrogen filling stations would be 3% of capital cost. In practice, the maintenance of filling stations in California turns out to cost 30% per year of capital cost, because it's very, very difficult, as I said, to compress and store and manage hydrogen. It requires exotic materials. It requires safety critical, high fidelity, pressurized systems, and they are very expensive to engineer. So the reality of hydrogen filling stations is that they are incredibly expensive. And if you look at the downtime of filling stations in places like California, 2 out of 3 filling stations are down most of the time because of these maintenance issues. That's the reality of hydrogen filling stations. So whereas electric chargers are solid state devices, once they're there and working, they're essentially working, and they don't have those high maintenance costs. So getting hydrogen to the filling stations is incredibly difficult. Let me give you one statistic about that. If you want to transport hydrogen in trucks, you do it in a what's called a tube trailer at high pressure, 700 bar, 700 atmospheres, very high pressure. And such tube trailers are expensive. They cost $1 million each. Now, if you want to transfer the same amount of energy as a diesel tanker, right? We fill up filling stations with diesel tankers. They weigh 40 or 44 tons in the whole vehicle. A 44-ton tanker, to replace that, to transport the same amount of energy in hydrogen, guess how many of those tube trailers you need for one hydrogen tanker? For one diesel tanker. Sorry?
16 times more?
18 times.
Yeah,
exactly.
Almost.
You need 18 tube trailers for every tanker. So if you think about that problem, I was just in Australia a couple of weeks ago, and there are these huge trucks carrying diesel through the outback of Australia, filling up filling stations. Huge trucks. They're triple trailer tankers. They're 55 meters long. They weigh 150 tons. They're enormous vehicles. And now you need, for every one of those, and you see them every now and again in these places which are very remote, for every one of those, you need 18. It's not going to happen. For every diesel tanker filling up a filling station, you need 18. It's not going to happen.
Otherwise, you need to electrolyze at the spot.
Okay, you could electrolyze at the spot. All right. So if you electrolyze at the spot and make the hydrogen there, then it's the same argument as before. You need 3 times more electricity to do that than to just charge the batteries. So you need a 3 times bigger electricity grid connection at your filling station than you would have if you just charged batteries of trucks coming in. So instead of needing, a 25 megawatt grid connection or something to charge trucks. You need a 75 megawatt grid connection to run an electrolyzer, to waste a whole bunch of energy making hydrogen so that you can waste 75% of it. So it doesn't make any sense. It costs a huge amount of money. Way more expensive to have a 75 megawatt grid connection and electrolyzer facility and hydrogen filling station than to have a 25 megawatt connection and some fast chargers, which is what you're talking about. And especially since that filling station, that hydrogen manufacturing facility, just the filling station part, we know that 30% of capital cost is being spent on maintenance every year to just keep the compressors running. So it's really hard, hydrogen, really, really hard. It's hard and expensive to make. It's hard and expensive to distribute, and it's hard and it's expensive to use in the vehicle. And that's the reality of it.
So that brings us to the topic of a so-called blue hydrogen. If it's not feasible to electrolyze and to make it green, there's probably, and as we see it now, there is urge. Let's do the blue hydrogen and carbon capture and so on. Can you expand on that?
I can, absolutely. So, there's so many different aspects of this that, first of all, if you do blue hydrogen, you still haven't solved the other two problems. I explained that there's three problems with powering hydrogen vehicles. Yeah. You've got to make the hydrogen, you've got to distribute the hydrogen, and you've got to have a vehicle that uses it. So that's three major engineering challenges, right? You've got to make the hydrogen vehicles, you've got to make the hydrogen distribution infrastructure, and you've got to make the hydrogen. Okay, so you can make blue hydrogen. It solves one of those. Instead of using such a large amount of energy to make green hydrogen, you use fossil gas to make blue hydrogen. Now, that, of course, is what the fossil fuel industry and most of the hydrogen lobby are interested in doing, is using fossil gas to make hydrogen. There's no doubt about that. That's their interest. In a way, I think they're using green hydrogen as a little bit of a trick, what you might call a bait and switch operation. What they say is, you go and you use hydrogen for heating and install those hot water heaters, hydrogen ready, install all those hydrogen trucks, and we'll provide the green hydrogen. Oh, sorry, it was too expensive to make green hydrogen. You can use this blue hydrogen or this gray hydrogen instead for all that infrastructure you've installed. So there is I think there's a big question as to what the motivation is of the fossil fuel industry. If you make blue hydrogen or gray hydrogen, when you make it from methane, from fossil gas. And the way you do it is you apply hot steam, very hot steam, to methane. It's in a process called steam methane reforming. And what it does is it splits off the carbon and makes it into carbon dioxide. The methane is CH4, a methane molecule. It's got one carbon atom and 4 hydrogen atoms. When you apply hot steam to it, the carbon gets made into CO2 and the hydrogen gets split off into hydrogen. It turns out that it's the carbon which has most of the density, energy density. Most of the energy in natural gas, in methane, is in the carbon. So what you do when you do that process, you strip off the carbon, you mix it with oxygen and put the carbon dioxide down a hole in the ground. You get no benefit from that energy, and you're left with the energy density of hydrogen, which is significantly less than the energy. The amount of energy left in the hydrogen is much less. So you have to use a lot more natural gas to deliver the same amount of energy, because you're taking some of the energy out of the gas and you're putting it down in a hole in the ground and getting no value from it. So you need to increase the amount of natural gas that you use when you go by this route by about 50%. All right, so 50% more natural gas. So that's a great story for the gas industry, of course, because instead of the demand for natural gas going away because we're not
Yeah.
using it for heating anymore, suddenly we need 50% more of it because we're going to use it for hydrogen. So that's a good story, there's no doubt, for the natural gas industry. Now, the problem with this is, well, there are many problems with it. One is that the natural gas itself is already a problem. Natural gas is not a clean fuel at all. It's actually a dirty fuel, and it depends where it comes from as to how dirty it is. And it's dirty because in the manufacture and supply, and in the production and supply chain for natural gas, there are a lot of what is called fugitive emissions. And that means natural gas which is being leaked deliberately or not, which is being vented deliberately or flared deliberately in the production of that gas. And that fugitive emissions of natural gas is thought to be up to about 3% of world production. At the point where it's 3% of world production, of course, the methane is has a very high potential, global warming potential, 25 times the global warming potential of carbon dioxide on a 100-year basis, but it only lasts in the atmosphere for a short time, and on a 25-year basis, it's 86 times worse than carbon dioxide. And that's the basis on which we should assess it, in my opinion, and many scientists think that. So at 3% fugitive methane emissions, when you account for the very high global warming potential of the gas, it turns out that natural gas is worse than burning coal in terms of its effect on climate change. So natural gas is already really dirty before you even start. And it comes from places like Kazakhstan, from Russia, from the Permian Basin in Texas, where there are very dirty practices and people, honestly, who don't care how much methane they're emitting. And it is a big problem, thought to be about a third of the global warming problem that we've got is methane emissions. So the same people who are selling that methane, that are making a third of the global warming problem, want to sell more of it, 50% more of it, to make hydrogen. And if they make 50% more of it, it's going to have 50% more fugitive emissions, unless that's cleaned up. So there's a real problem there in fugitive emissions of methane before you even start to make it into hydrogen. There's
with
other...
With the current state of technology, can it really be cleaned up?
Well, that's an interesting question. I think it's an economic problem. I think it can be cleaned up. In many, many cases, I'm told that it can be cleaned up with positive economics. That is, you make more money by selling the fugitive methane than it costs you to clean up the leakage. However, that's not how business works, right? Business doesn't work that way. Just because it's got a positive business case doesn't mean they're going to do it. The problem is that if you've got some money to spend, in general, it's going to be much more profitable to spend that money opening up a new gas field or, building some new production than it is going to be to clean up what you're already doing. So the priority use case for the money is building new uses, not cleaning up existing uses. And until there is some really serious legislation forcing companies around the world to clean up their methane production, there's no reason for them to do it. And it's not just in the US, and it's not just in Norway. It's in, as I say, Russia, it's in Kazakhstan, it's in all kinds of places, that in Qatar, that make gas where, frankly, the manufacturers who are distributed. They're small, lots of small companies who are producing gas. They don't care, and they're not governed by any legislation that matters. So that problem has to be solved first before you start talking about using 50% more natural gas to make hydrogen, if you're interested in the energy transition, if you're in decarbonizing the planet. And as I say, it's thought to be about a third of the global warming problem, caused just by companies that don't care, really, gas companies that don't care, and that are venting, flaring, and leaking enormous amounts of methane. Okay, so let's just assume for a minute that we can solve that problem. And there are initiatives. There was a big initiative from COP26 in Glasgow with the Americans and Chinese and so on, saying that they're going to fix methane emissions. Well, there's no sign of it really happening. But several years later, just suppose we could solve that problem. Then your other challenges are to capture and store the carbon emitted from your hydrogen manufacturing process, to convert your grey hydrogen process, where you just let the carbon dioxide go into the atmosphere, to convert that into a clean blue hydrogen process where you capture all that. Sorry, I said hydrogen going to the atmosphere. I meant carbon dioxide going to the atmosphere.
Yeah.
Where you capture all that carbon dioxide and you sequester it underground. So what are the problems with doing that? Well, the first problem is it's incredibly expensive, and somebody has to pay for it. All right, that's the first problem, and there's no sign of anybody going to be paying for it. So if you can make your hydrogen grey and vent the carbon dioxide at no cost, but it's going to cost you a lot of money to capture and store that carbon dioxide, why would you do it? All right, there's no reason to capture and store the carbon dioxide unless there's a strong incentive, and that has to be a tax or a penalty or something. Those taxes and penalties do not exist. There's a policy problem there to make it worthwhile for somebody to make blue hydrogen. But they've got to be big incentives because it's very expensive. There's two parts of the problem. The first part is to capture the carbon dioxide, and the second part is to store it. The capturing itself has two problems. One is that, and what that means is that in practice, it's very expensive to capture more than about a half of the hydrogen, of the carbon dioxide.
Yeah.
It's very, very increasingly expensive the more you want to capture. So that's a problem. So typically, the plants that exist, the pilot plants, is one in Canada, one in Australia, for capturing carbon from hydrogen manufacture. They only capture about a half, if that. In fact, in the one in Canada, it captures half of a half. Half of the emissions are from the chemical process. Half the emissions are from making that steam. When you make steam, that generates combustion gases where it's very hard to capture the carbon dioxide, and they don't bother with that. So they capture half of the process emissions, half of the emissions. It's about 25 or 30%. So all the rest goes into the atmosphere. So there's a problem there in capturing the actual chemical process, capturing the carbon emissions. The other problem then is it's very expensive to pump it somewhere where you can sequester it safely forever down a hole in the ground. And that just doesn't come for nothing. You have to pay for that. You have to pay for the hole in the ground. You have to pay for the pumps, the pipes, and the process of sequestering and capturing and that carbon. And it is expensive.
How far are we from a climate catastrophe? Because from everything that you have said, I'm really worried with that question because no real changes are taking place.
I'm not the expert on climate science, so I can't really give a comment other than what we read. The 1.5 degree point, which is considered by many people to be the sort of approximately safe point, we're about to go past that now. There's no chance that we're going to stay within 1.5 degrees. Will we be able to stay within 2 degrees or 3 degrees? That's very hard to say. At the 1.5 degree point, you get to various climate tipping points, which can cause the problem to run away. So, yeah, it's really, really worrying. And the solution is to do stuff right now, to move as quickly as we possibly can to solutions right away. And they are electrical solutions. There are electrical solutions that exist for electric cars, for example. If you can do an electric car now, then that's what you should do. You shouldn't wait until 2035 until a hydrogen car may or may not be ready and delay your transition. You should just do it now. If you can install a heat pump in your house now, then you should do that. You shouldn't wait till 2035 or 2040 until somebody works out how to mix single malt whiskey into your petrol tank, how to mix very expensive green hydrogen into a gas pipeline so that you can run it on gas. Because, it's never going to happen, is my opinion, that it's never going to be cheap enough to heat houses and to
When you said
vehicles.
when you said now, it's really now, because I've talked with one climate expert, and he told me that everything that's happening today is the consequence of things we did 20 years ago. So basically, everything that we change today will have an effect in 20 years.
That's right. The carbon, emitted carbon, that's absolutely right. It stays in the atmosphere forever and it builds up, and that's exactly right. That's exactly right. So there's a long half-life, a long time taken. It's everybody's responsibility to move as quickly as possible with the energy transition. And so I have a big problem with companies whose motivation is to try to maintain their existing fossil fuel market by telling everybody that they're going to make clean hydrogen by, carbon capture and storage, clean blue hydrogen, when what they're really trying to do is maintain their market for fossil fuels. That causes me a problem. As somebody who's concerned about the environment, I have a big problem with that. And I think part of that strategy is, as I've said, sell green hydrogen as the solution, get people to convert their appliances and their vehicles, and then, we're really sorry, it's too expensive to do green hydrogen. You just have to use this grey hydrogen instead. Or maybe we'll make some blue hydrogen sometime when we get carbon sequestration, CCS, to work. But by the way, we've been talking about CCS for 40 years and we haven't got it to work anywhere, really.
Are these companies aware? I'm referring back to the case of ExxonMobil, what they knew 50 years ago or so. Are they aware, and do they care?
Are they aware of what?
Of the potential consequences of this?
Well, you have to ask them. I think they knew long ago that this was going to be a problem, that global warming is going to be a problem.
Yeah, exactly.
They know it's a problem now. For one reason or other, they push hydrogen as a solution. Maybe they think it's really a solution. Maybe it's a delay tactic. If they think it's a real solution, I'd ask them to look at the science, because when you look at the science of the thermodynamics, it's quite clear to me that it's not a solution at all. And I don't believe, they've got plenty of smart engineers in those companies, in the fossil fuel companies. They're full of R&D capability and people who are able to do the same simple calculations that I can do. So I don't believe that they don't know. If this is a delay tactic on their behalf, well, the whole world is going to suffer. And I think that's a very cynical thing for them to do. I think it's, I can say cynical. I could say some much worse adjectives.
So let's go back. We totally went off script. Let's go back to the technology. What are the most significant technological hurdles for hydrogen to become a viable and sustainable energy source? Is there a way that technology can solve its problems in future?
Well, it's a good question. As I said before, there's three problems with hydrogen.
Yeah.
It's difficult and expensive to make, it's difficult and expensive to transport, and it's difficult and expensive to use. And they're the only three problems. And each one of those problems requires massive engineering miracle to solve. So that's the problem. Hydrogen is essential in some applications. And so we need it to be as cheap as possible. Green hydrogen is essential. And we've said what those applications are. They're fertilizer, they're petrochemical processing. It may be that they include manufacture of steel, which is an absolutely massive, 8% of world carbon emissions is manufacture of steel. That's a really huge application. It may be that it will be in manufacture of sustainable aviation fuels. And that's, again, a big, not nearly as big as steel, but it's a big application. So there are some applications which are really essential, some which are quite likely, and we really have to focus on those. We shouldn't be focusing on anything that can be electrified. We absolutely shouldn't be focusing on powering of trucks and cars. We shouldn't be focusing on powering of heating systems. These are just mad, crazy applications which are never going to work because they're so expensive and so efficient, and where there are electrical alternatives. So what technology developments are needed? There's undoubtedly green hydrogen needs to be cheaper. Green hydrogen manufacture needs to be cheaper, but it needs to be used for those applications for which it needs to be used. It will be manufactured on site. It will be used to manufacture fertilizer. It will be used for petrochemical processing, be used for manufacture of steel. It's not going to be pumped around houses to heat houses or to filling stations to power trucks. Just not. It's so expensive to do that compared to electrical alternatives that it's never going to be cost effective. So we need to focus on the important use cases and focus on the manufacture of hydrogen at centralized locations for those uses. Focus on the manufacture, not the distribution, and not the use cases which are going to be unsuccessful. So that's my advice. Absolutely focus on electrolysis, electrolyzer manufacture, to some extent on storage of hydrogen. Focus on that. Do it where you need to use it, and forget the other issues of pumping it around the world, pumping it across Europe, trying to transmit it in liquid hydrogen tankers from Australia to Japan. All those things, they're mad. They'll never work. It's way too expensive.
We are out of time, but this definitely requires a round two. David, it was my pleasure. Thank you so much.
Good. Well, I hope it's been useful, and will help refocus people on the important applications and the important job that we have to do to decarbonize the planet.
Hope so. Thank you.
Thanks, Amos. All the best.